Good evening, everyone. I am Peter Kariva, and president of the Aquarium of Pacific, and I want to welcome you to our Aquarium lecture series. I'm delighted you're here virtually. I'll be even more delighted when you could be here in flesh and blood. But before we move on to the lecture, I want to thank our sponsors. This is only possible with them, the Gazette newspapers and Courtyard Marriott. This evening, we're very fortunate to have Dr. Jeffrey Bennett, and he's going to be talking about global warming, the science behind it, and the impacts of it. He's written a terrific book on this that I used when I was a professor at UCLA called A Global Warming Primer. And while we're all mired in this pandemic, we're also coming to grips with societal racism. We can't lose sight of the fact that global warming is truly an existential crisis, and we have to address it. Now, our speaker, Jeffrey Bennett, has a PhD in astrophysics. He's something of a polymath. He's written four college textbooks, one in astrobiology, one in mathematics, one in statistics, and astronomy. And on top of that, if you go to his website, he's produced a series of children's books, and I want you to take a note of the URL, because if you go directly to that and purchase those children's books on science, and they're terrific, the money, the proceeds from it are going, for this year, are going directly to the National Urban League to support education for minority students. So with that, I'm going to turn it over to Dr. Bennett, and I look forward to having climate science and climate change demystified.
Thank you very much, and Peter, welcome to the Aquarium. I'm sorry I'm not there to meet you in person, but I'm sure you're excited about the new position and all the wonderful things that the Aquarium has been doing for outreach and education and science, and I really appreciate that. I wish I was there in person to be with you all, and perhaps we'll be able to do that some other time. But one advantage we get here with the virtual approach is I can be floating above the earth, which I wouldn't be able to do in the live lecture format. So thank you for listening in. And what I want to do tonight is, the title you can see is Global Warming Demystified, answering your questions about the science, the consequences, and the solutions. And my goal is to try to help you understand the basic science behind this problem, and then talk about why, even though I hope you'll agree with me that it's a real problem and a scary problem, it does have solutions, and I'll spend some time talking about that. And I'll just point out briefly, Peter showed a copy of the book. Thank you very much, Global Warming Primer. And you see on the screen here the URL for it, and the entire book is actually posted there for free, so you can read the book online if you'd like. So to get us started, I want to just talk about what we're talking about when we talk about global warming. And certainly there's impacts we're feeling now, and we'll talk about that. But mostly we're talking about the future. So I want you to think for a moment, what do you think about when I ask, what is the future? What are you thinking about right now when I say, what is the future? And in general, when I've asked this question to various different audiences, what I find is most people are thinking with a fairly short horizon. In fact, probably right now, you're thinking about the future is, when will this pandemic be over, and when can we get back to a more normal life? And if you're in high school, you might be thinking about what you'll be doing in college, your first job, and so on. And when we talk about the future in the context of global warming, we're usually talking about predictions and projections. And if you read the media reports, you'll often see them projecting, here's what might happen by the year 2030. Here's what might happen by the year 2050. But it's actually kind of rare to see the time frame going beyond that. And that's something I want you to think about, because if you are a kid in school today, or if you have kids or grandkids in school today, and if they live like my grandmother did to be 100 years old, which will probably be very common by later in this century with advances in medicine, that means that today's school kids, or your kids or grandkids in school, are likely to still be alive in the year 2100 and beyond. And you'll notice that's way beyond the time frame that we're usually thinking about, that the media is usually reporting on for global warming. And it's important, I think, when we talk about this topic, to enlarge that time frame and start thinking to the year 2100 and beyond. And I want you to keep that in mind as we go through everything else. But for the moment, let's get into the basic science of global warming. I'm an astronomer. I like to approach this topic from an astronomical perspective, which in fact, historically, is where the topic kind of began, not entirely, but at least partially. And what you see here on the screen is I've put photos of the Earth and Venus, and I've put them on the screen to scale. And what you notice when I do that is, well, they're the same size. Within just a few percent, these two planets are exactly the same size. They're also, from other things we know about them, if you were to cut them open and look inside them, they would probably look just about as similar as it's possible for any two planets to look. In other words, for most practical purposes, Earth and Venus are as close to being twin planets as you can get, with one exception. And that one exception you see here on the screen is their global average surface temperature. On Earth, we have this very pleasant global average surface temperature, whereas on Venus, 470 Celsius, 880 Fahrenheit, that's hotter than a pizza oven, hot enough to melt lead. And what I'd like you to think about when you're thinking about the basic science of global warming is to try to think about it the way a scientist would go about thinking about it. And if you think about this like a scientist, what you might wonder is, why would two planets that are almost identical twins have this one major difference between them? And you probably know that in science, the way we go about answering a question like this is we form a hypothesis and then we test it out. And the first hypothesis that occurs to most people is that Venus is closer to the sun than Earth, which it is. But it turns out if you test that hypothesis very closely in detail, you find the distance alone will not explain this difference. And one way you can see that is by looking at the solar system to scale. So this is the Voyage scale model solar system in Washington, D.C. We have these models in a few other places as well. And there you can see the sun at 1/10 billionth of actual size, and then Mercury is over here. Venus and Earth on this scale are both the size of the ballpoint in your pen. And what you'll notice is, imagine you put a big bonfire here where the sun is located, and then you go stand over here by Venus, then you go stand over here by Earth. Well, of course, you would expect it to be warmer at Venus because you're closer to the bonfire, but it's not going to be enough warmer to account for this huge difference in temperature. And quantitatively, we can calculate it out and we'll find the same thing. Distance won't explain it. In fact, there's actually another part that's even more interesting, which is you'll notice the clouds on Earth, and clouds reflect sunlight. And then you look at Venus and you see it's completely covered in clouds, which reflect a lot more sunlight, therefore, than Earth's limited clouds. Excuse me, I need to go back there. And as a result of all those clouds, less sunlight actually reaches the surface of Venus, even though it's closer to the sun, which means that if it were just distance and cloud cover, Venus would actually be colder than the Earth. But it's not. So we still have our mystery. Why is Venus so much hotter than the Earth? And we could hypothesize further, which we would do if we were in a science class. But for now, I'll just tell you the answer, which is what we call the greenhouse effect. And you're probably familiar with how the greenhouse effect works. The light that warms any planet, including the Earth, is coming in primarily in the form of visible sunlight absorbed down here on the ground. And the ground has to return that energy to space. Some of it is reflected back by the ground or by clouds, but some of it is absorbed, heats things up, and then the ground returns that energy to space in the form of infrared light, represented by these red squiggly arrows here. And what you'll notice is there's these blue dots in the atmosphere, and those are what we call greenhouse gas molecules. And the three most important greenhouse gas molecules on Earth are water vapor, carbon dioxide, and methane. And what happens is when infrared light hits one of these greenhouse molecules, it gets absorbed, it gets re-emitted, and the net result is that the more greenhouse gas you have, the more difficult it is for this infrared light to ultimately get that energy returned back to space. So in other words, it kind of keeps this heat and energy trapped. These blue dots keep it trapped down here, making the surface, the oceans, the lower atmosphere warmer than they would be otherwise. A good analogy you can think about to this is a blanket. If you're outside on a cold night and you wrap a blanket around yourself, what you'll find is you get warmer. But think about that. Why do you get warmer? The blanket doesn't give off any heat. It's just a piece of cloth. So how does it warm you up? It's because it's slowing the escape of your own body heat. And that's the same thing that the greenhouse effect is doing for Earth or any other planet. It's slowing the escape of the planet's heat and therefore making the surface and lower atmosphere warmer than they would be otherwise. Now, I told you I want you to think like a scientist. And so I've told you this is the answer to this mystery of Venus and Earth, which we'll get into the details in a moment. But if you're thinking like a scientist, scientists are always very skeptical when they're told something like this. And so the question that you should ask if you're thinking like a scientist and you don't know a lot about this already is, how do you know that this is real? Why should I trust you about the greenhouse effect? And the answer is because we have scientific evidence that makes it very clear. And there's two basic lines of evidence that show us that the greenhouse effect is real. The first is we can actually measure it in the laboratory. You essentially put gases in a tube, shine light of different wavelengths at it, and measure how the gas affects that light. And these measurements are not new. This has been done. The first known measurements were done in 1856 by a woman named Eunice Newton Foote. In fact, by the late part of the 1800s, 1896, famous Swedish chemist Svante Arrhenius had already used these measurements to calculate what would happen if the amount of carbon dioxide in our atmosphere was doubled. And by now, the measurements are so sophisticated that we know exactly how all the various different gases in our atmosphere interact with all the different wavelengths of light. And what that means is that scientists can use that data to quantitatively predict what should happen with a planet. And that brings us to our second line of evidence, which is that you can actually check on real planets. You compare the predicted temperatures based on those laboratory measurements with the actual temperatures. And what you find is that when you do that with the predictions made based on your laboratory measurements of the greenhouse effect, you get correct answers. But if you do it any other way, you don't get correct answers. So that validates that the greenhouse effect really does work the way we have measured it to work. And it really is the answer to what makes the planets warmer than they would be otherwise. And it's very important to realize that this is a very important and strong effect. For example, even on Earth, where we don't think about it that much, the natural greenhouse effect is very important because without it, right here you see a calculation showing what the temperature of the Earth would be without the greenhouse effect. The temperature would be negative 16 degrees Celsius, which is way below freezing. In other words, without the greenhouse effect, we wouldn't be here on Earth. And that brings us back to our tale of two planets. We can conclude it now. For the Earth, we have this nice, pleasant temperature rather than being below freezing because we have enough carbon dioxide in our atmosphere to make our planet livable. Remember, without that, it would be frozen here on Earth. And therefore, the greenhouse effect in its naturally existing form is a very good thing for life on Earth. But now what's going on with Venus? Well, it turns out Venus has about 200,000 times as much carbon dioxide in its atmosphere as Earth. Back to that diagram I showed, that's like 200,000 times as many blue dots. And that is what causes Venus to have this extremely high temperature. And what I like to have you think about is what this is showing is that if the greenhouse effect is a very good thing for life on Earth, as we see that it is, Venus is basically proof that it's possible to have too much of a good thing. And that brings us to why we have scientific concern about global warming. Because here we have absolute proof that more carbon dioxide means higher temperatures. And we know that human activity is adding more carbon dioxide to our atmosphere. And here's a very famous graph that you may have seen showing how we know that the carbon dioxide concentration is going up. These are direct measurements of the concentration of carbon dioxide in Earth's atmosphere, which were begun in the 1950s by Charles David Keeling at the Scripps Institute of Oceanography. The units here, parts per million, that's telling you how many molecules, out of every 1 million molecules of air, how many of them are carbon dioxide. And what you see is that when he started making those measurements in the late 1950s, about 315 out of every 1 million molecules was carbon dioxide. But today, we're 100 more than that. We're up to 415 parts per million of carbon dioxide. So that is a very substantial increase. Now, you might wonder, how do I know that this is due to human activity, like the burning of fossil fuels, and not due to some natural phenomenon? And I won't go through it here, but if you go to the website, globalwarmingprimer.com, I give you the 4 key lines of evidence that all point clearly to the fact that this is our carbon dioxide coming primarily from the burning of fossil fuels. And so once you know that we're adding carbon dioxide to the atmosphere, and that more carbon dioxide means higher temperatures, you realize this could be a potential problem. One question that you might still have, though, is how high is this really? How does it compare to what's happened on Earth in the past for natural reasons? And to answer that question, you would want to have data that takes you back earlier than when people were measuring it in the 1950s. And at first you might think, well, that's going to be hard because nobody was measuring it. But it turns out there's a number of different ways that scientists can figure out what the past carbon dioxide concentration was. And one of the best comes from these things that we call ice cores, where the scientists go down to Antarctica, they drill down into the ice, they bring up drill bit shaped tubes of ice that they cut into slices so that they can lift it over their heads for fun. And then they take these, they store them in laboratories, they study them. But if you look closely at these ice cores, what you'll see is that they're made up of layers. And what are those layers? We have to think about where the ice in Antarctica came from. And that ice in Antarctica came from snow that fell and piled up year after year after year. And as a result of that, you can actually see the layers in the ice cores year by year. So it's almost like counting tree rings to figure out how deep into the past you're looking in an ice core. And one of the most remarkable scientific achievements, in my opinion, of all time, is that a group of researchers has gone down to Antarctica. They did this a little over 10 years ago, and they drilled more than 2 miles down into the ice. And at the bottom of that ice core, after you count through the layers, you realize you're bringing up ice that represents snow that fell 800,000 years ago. And as a result of that, we now have an 800,000-year record of the carbon dioxide in Earth's atmosphere because there's air bubbles trapped in these ice cores. So you measure the carbon dioxide concentration in those trapped air bubbles. And this graph is showing you the data. So you can see it says thousands of years ago. So here's the present, 0, 100,000, 200,000, 300,000, back to 800,000 years ago. And what do you notice about the carbon dioxide concentration? Well, the first thing you notice is it varies a lot. And this is all natural variation. We humans didn't have anything to do with this. But the second thing you'll notice is that during these 800,000 years, it varied from about 180 parts per million to about 280 parts per million. In fact, in the year 1750, which kind of represents around the beginning of the Industrial Revolution when we started to burn more fossil fuels, the concentration was about 280 parts per million. Since that time, it has shot up. There is the zoom out of the last few decades that you already saw, so that we've gone from never being above 280 parts per million in the past 800,000 years to to 415 parts per million today, which means we're now about 45% higher than any time in the past 800,000 years. Moreover, if you extrapolate this up and say, well, if we keep behaving as we are, keep burning fossil fuels the same way we are today, when will we be up to double the pre-industrial value, up to 560 parts per million? And you'll find that's only about 50 or so years away from now. In fact, if we keep going like this, we'd be at triple that, approaching 1,000 parts per million by the middle of the next century. And so we can see that we are changing things in a big way in terms of how the carbon dioxide concentration in our atmosphere is compared to what it has been, at least for the past 800,000 years or so on Earth. And so we can take these ideas and summarize them. And the way I like to do this summary is in 3 steps: global warming 1, 2, 3, and makes it easy for you to remember the basic science of global warming. So number 1 is, it is a fact that carbon dioxide, which is a greenhouse gas, makes Earth warmer than it would be otherwise. There's no scientific doubt about this fact at all. I showed you how we know it through the evidence from the laboratory and planets. Number 2, it's also a fact that the use of fossil fuels is adding carbon dioxide to our atmosphere. I showed you the data proving that that's the case as well. And that brings us to number 3, which is that if we know more carbon dioxide makes planets warmer and we're adding more to the atmosphere, then global warming is going to occur. It's inevitable. And that is why scientists are so concerned about this. There's no scientific doubt that this is a real thing. And we can further confirm it by looking at the data. Here we see the theoretical reason why we know global warming should occur. And here you see it is in fact happening. This is the temperature record going back to 1880, which is as far back as we have reliable temperature records for. And compared to the 20th century average, this line here, and you can see it's quite clear that the trend is, just as we expect from the 1, 2, 3 science, the Earth is warming. And that brings me to a side note here, which is, given how simple and easy it is to understand this basic 1, 2, 3 science of global warming, why is it that so many of our political leaders have seemed to have difficulty understanding it? And to address that question, I want to ask you to think about, maybe some of you know, maybe you don't, I can't poll you in person, but who do you think was the first major global leader to get on the international stage and say, basically, look, this is simple. 1, 2, 3, we're going to cause global warming through our actions and we need to do something about it. And now that you've thought about who you think it is, I'll tell you the answer that surprised most people. The person who first made a speech about this to the United Nations was Margaret Thatcher, the British Prime Minister, known as one of the founders of modern conservatism. She did it in a speech in 1989. If you go to the globalwarmingprimer.com website, I have a link to the entire speech, which is worth watching. But look at what she said. She said, "What we are doing now to the world by adding greenhouse gases to the air at an unprecedented rate is new in the experience of the Earth. It is mankind and his activities which are changing the environment of our planet in damaging and dangerous ways." And you can see she has it exactly correct. She's got the science there. She says it's real. She says it's serious. She goes on in the speech to talk about how we need to deal with it. And if anyone ever tries to tell you that this issue is somehow a liberal versus conservative kind of thing, you can just point back to this and show the first person, the first major political leader to speak out on this on the international stage was one of the founders of modern conservatism, Margaret Thatcher. And just in case some of you were wondering, well, yes, that was conservatives back a few decades ago. What about today's conservative leaders? What would Donald Trump say about this issue, for example? Well, it turns out Donald Trump actually paid to the New York Times to have them put in a statement that he and some other business leaders wrote. Here's what he wrote. If we fail to act now, it is scientifically irrefutable that there will be catastrophic and irreversible consequences for humanity and our planet. So I'll let that sink in for some of you for a moment. But what you can see is, at least sometimes, there should not be any debate about the science behind this topic. It is, as Donald Trump said at this time, scientifically irrefutable that this is a real issue. Given that, you might wonder, how does anyone still argue against this? And I won't spend much time on that here today. In the book, I go through all of the major skeptic arguments, but I want to just point to a couple of them. The first one is, you may have heard people say, well, maybe it's the sun that's causing this rather than human activity. But you can see here a graph. This is the same temperature data I showed you before, but smoothed out. This is this amount of energy we receive from the sun. And while they track together fairly nicely from 1880 to the mid part of last century, you can see in recent years the temperature keeps going up. The sun's gone in the other direction, which means it cannot possibly be the sun. Another common argument, one that you might hear made by some of the so-called scientific skeptics of climate change, is that, well, yeah, it's warming up, but what's the big deal? The climate changes naturally anyway. And so I want to go back to that ice core data and show you what the big deal is. Because before I showed you this, the carbon dioxide concentration going back 800,000 years, here's the global average temperature from the same ice core record. And you'll notice that the temperature varies quite a lot on Earth over this time. All these dips are ice ages, and the peaks are the interglacial periods, like the one we're in right now. One of the things you'll notice is that they correlate. When the carbon dioxide concentration is high, so is the temperature. And when it's low, so is the temperature. Why? Because that's just the 1, 2, 3 science again. They go together. And what you'll notice is that because we always expect there to be a delay in the temperature response compared to the carbon dioxide response, if the temperature keeps going up in the same way that the carbon dioxide has been going up, that looks like a pretty serious consequence. And that means, rather than making us feel good that, yes, the climate changes naturally anyway, this should actually make us more concerned, because we have past evidence showing that what we are doing with carbon dioxide in the atmosphere is very likely to drive the temperature considerably higher than it is today. And of course, we use scientific models to try to predict exactly how much higher we'll go. And that is indeed where a lot of the concern comes from. So now I want to turn to the consequences of global warming. And what I'm going to do for you is try to break down all of the major consequences of global warming into 5 basic categories, just to keep it simple and easy to understand. The first of these categories is what you might call regional climate change. And this is just the idea that, well, when I say global warming, we're talking about the average temperature of the Earth increasing. But of course, different places might warm more or less than average. And that's one of the reasons why a lot of scientists refer to this topic as climate change rather than as global warming. The two terms are basically interchangeable. And here's a map that NASA has put together showing temperatures around the world. You can see down here it shows 1880 to 1884. This is for each place relative to its 20th century average. And when I click again, it should start the video running. And so you can see, now it's going to go, the years going by here and the changes. And you'll notice as we go into the beginning of the 20th century, some places get warmer, some places get cooler, but it looks almost random. But as you keep watching and we get to the latter part of the 20th century, you'll notice it starts not to look quite so random anymore. And here we see the latest data, and you can see it's very striking. The entire Earth virtually has been warming up, some places much more than others, particularly up in the Arctic regions. And so this is real, it's happening, and it has a lot of effects. Excuse me, I'm having trouble getting, there we go. There's our next slide. One of the effects that a lot of you are probably noticing right now in the summer is that it also changes the number of days we have with different types of temperatures. So this graph shows you, made by James Hansen, and it shows you a normal distribution of temperatures for the period 1951 to 1980. I won't go into the details, but basically what Dr. Hansen did was he took temperatures from all land regions in the Northern Hemisphere, normalized them to one curve. So you see most days are what we call normal. Some days are cooler than normal, some days are hotter than normal. A small number are extremely hot or extremely cold compared to the normal for summertime. And now you see the same data for 2005 to 2015. And you notice the whole graph has shifted to the right so that today's normal is what we were calling hot just a few decades ago. And you might have heard, for example, that down in Phoenix, they've already broken the record this year for the most days over 110 degrees. And that's a reflection of what you see right here. This regional climate change has many other effects. Where I live in Colorado, we have a wildfire burning on the western slope right now. I know you're in California where there have been many, many bad wildfires recently. These things are happening because of regional climate change, or they're being made worse because of regional climate change. The second consequence of global warming is an increase in storms and extreme weather. And this one's very easy to understand. Remember what the greenhouse effect is doing. It's trapping heat and energy down in the oceans and the lower atmosphere. And you probably know heat and energy are what drive weather. And therefore, with more heat and energy, we expect more extremes of weather. And we are seeing that. This is a graph showing you the number of global extreme events. The red you can ignore at the bottom, that's like earthquakes and volcanoes, but all the rest is climate and weather related. And you can see very clearly the number of extreme events is indeed going up. The third major consequence of global warming is the melting of sea ice. Remember that the Arctic Ocean has a lot of ice in it, and the Arctic is the region that's been warming the most. And as a result of that, a lot of that ice is melting. Now, when I talk about the melting of sea ice, it has nothing to do with sea level rise because this ice is already floating, so it does not have a major effect on sea level. But it does have many other effects. It increases the salinity, decreases the salinity of the water locally. And one of the most worrisome effects it has is that ice reflects a lot of sunlight. Water absorbs most of the sunlight that hits it. And therefore, as the summer ice coverage has gotten reduced, and you can see it both in a graphic here relative for these 3 years and the general trend going downward over time, as we reduce the amount of ice, that means more sunlight's being absorbed and less is being reflected, which is going to amplify all the other effects we see of global warming. So that's a very worrisome concern with the melting of sea ice. And these changes have also been tied to changes in the jet stream, the polar vortex, and may, ironically, be even responsible for some of the very cold winter weather that we've experienced in the northeastern United States and parts of Europe in recent years. The fourth major consequence is rising sea level. This is actually happening for two different reasons. The first is water actually expands a little bit when it's heated up. And this effect, you'll never notice it in a cup of water or a cup of iced tea like I have here. But in the oceans, it's enough of an effect that it's already caused sea level to rise almost a foot in the past century or so. But the second and even bigger potential contributor to sea level rise is the melting of ice from Antarctica, Greenland, and other land-based glaciers, because when that ice melts, it flows into the ocean and causes sea level to rise. Now, scientists are actively studying the ice to try to understand exactly how fast we can expect it to melt. It's not very well understood yet, but it's very likely that we'll have a 1 meter, about 3 feet rise in sea level by the end of this century, by 2100, when today's kids will still be alive. And this map shows you, for example, in the southeastern United States, the red is regions that will be flooded by that 1 meter sea level rise. So if you have kids living in southern Florida or down here in Louisiana, the places where they now live, where they may hope to still be living when they're 100 years old, may not actually be livable by that point. And the yellow shows you a 6-meter rise. That could happen by the end of the next century. And one of the interesting things to think about is what could be the long-term consequence of this. And if we were to melt all the ice at Greenland and Antarctica, sea level would actually rise by about 70 meters, more than 240 feet, about 240 feet. Now, that won't happen quickly. It would probably take at least a couple of thousand years. That means on the positive side, there's time for people to migrate, if this happens, to migrate inland instead of being in flooded regions. But it gives you this kind of interesting mental image of our descendants in a couple thousand years needing deep sea diving equipment to visit the ruins of today's coastal cities. Going on to our fifth major consequence is what we call ocean acidification. And I know, since I'm speaking to an audience for the Aquarium of the Pacific, this is of particular concern for anyone who's paying attention to the oceans. The oceans are warming, which is a problem because the temperature changes affect fisheries and coral reefs and so on. But in addition to that, some of the carbon dioxide we're releasing into the atmosphere is being absorbed by the oceans, and that makes the ocean water become more acidic as well. And so this problem of ocean acidification is a very, very serious one. And we need to pay attention to it, even though it's not the one you hear the most about, unless you happen to be at an aquarium. It is at least as important, maybe more important in some ways, than all of these other consequences. And together, these consequences are all happening now. They're happening in a big way. They're serious. And they're going to keep getting worse. And how much worse depends on how much carbon dioxide and greenhouse gas we keep pumping into the atmosphere. And that brings me to the part of the talk where I want to talk about what can we do about this? How can we solve it? You can see the disclosure on the screen. I believe that up till now, everything I have told you is an indisputable scientific fact. Now, because I'm going to talk about solutions, you're going to start hearing some opinions mixed in with what I think are some real facts as well. So just be aware of the change. But it's very important to think about this solution because, again, remember our kids, grandkids, today's school kids who are still going to be alive in the year 2100 and beyond. They will face very, very serious consequences unless we do something to solve this problem. And the good news is we can solve it. In fact, we already have all the technology needed to solve this problem if we wanted to. In other words, we could replace all our current use of fossil fuels, and remember, they're the primary cause of this problem, with the combination of these three existing technologies that you see on the screen: efficiency, renewables, and nuclear. And we'd have just as much energy benefit as we have today without putting any more greenhouse gas into the atmosphere. And what are these three technologies that I referred to? Efficiency, you might not think of that as an energy technology, but it is, because if you can get the same amount of light with a light bulb that uses less energy, or drive the same distance with a car that requires less fuel, then you're getting the same benefit for less energy use. So that actually helps reduce our need for fossil fuels or any other form of energy. Renewables like wind and solar in particular, there is a lot of potential energy there. There are some challenges with storage and batteries and so on. And nuclear energy, which has been very controversial, but is safer and cleaner than fossil fuels by any measure. Just to give you a couple of examples, the amount of toxic waste that you get from a nuclear power plant in a year is equivalent to what you get from a coal power plant in about an hour. And because they don't put out pollution, you would prevent some 10 million, I'm a little trouble with my PowerPoint. You would prevent some 10 million annual pollution deaths that occur around the world from fossil fuel related air and water pollution. And nuclear energy does not produce any greenhouse gases. And I'm not telling you we need to do this necessarily. I'm just saying that between these three things, efficiency, renewables, and nuclear, if we wanted to, right now, we could replace all our current fossil fuel use with these with no impact to our lifestyles in terms of energy. I also want to say a few words about future technologies that are coming along that have even more incredible promise. For example, carbon neutral biofuels, which could be used for such things as ships and airplanes, in case you're wondering what we do about them. Solar energy from space, you know, a picture of these solar panels up in space in this painting here. It's never cloudy in space. And it's never nighttime in space if you face them towards the sun, so you can have the energy beamed down to Earth. Nuclear fusion. Our current nuclear power plants use fission. They split big atoms like uranium and plutonium. Nuclear fusion is what the sun does, fusing hydrogen to helium. We unfortunately do not know how to do this in a controlled way yet, but people are working on it. And it's worth thinking about the potential. For nuclear fusion, since the fuel is hydrogen, you could in principle get it from water. And if I turned on your kitchen faucet and let the water run through it, and then attached, you know, if you remember the Back to the Future movies, Mr. Fusion to that faucet, and let the Mr. Fusion extract the hydrogen from the water as it runs through, it turns out that from your one kitchen sink, the water running through that one faucet would produce through fusion enough energy to power the entire United States, which is truly mind-boggling to think about the amount of potential energy that we could have in the future if these technologies come to pass. And now we get to the question of, okay, if we know how to do this already and we have better technologies coming on in the future, what's stopping us? And the answer, I believe, is economics, and in particular, what I refer to as the socialized costs of fossil fuels. Now, you'll hear economists talk about this as the externalized costs of fossil fuels, but they're socialized because they're costs that we all pay as a society, even though we don't pay them when we go to the gas pump, for example. The health costs, the defense costs, subsidies and tax write-offs, the fact that a lot of terrorists have gotten their money from oil revenue and so on, environmental damage. And if you put it all together, according to a number of different studies that have been done, the total subsidies that we have for fossil fuels through these socialized costs for the United States amount to about $1 trillion a year. For the globe, about $4 trillion a year. And that's before you even count the effects of global warming and what that might do economically in the future. And so, to me, this argues the fact that we are using a false energy economy today. We think fossil fuels are cheaper because when we go to pay for them, they're cheaper than some of these other alternatives that I've talked about. But in fact, they're actually more expensive because when you factor in these other amounts that we end up paying, there's a lot more money. For example, if you took this amount and divided it over our current gasoline usage, you would need a gas tax of about $6 to $8 a gallon or more to make up for this $1 trillion a year subsidy. And so that brings us to what I believe is the simplest and easiest solution to this problem. And when I say I believe it, it's because I heard the idea from economists who are almost universal in agreeing that this is the simplest solution. And it's to put on a carbon fee or tax so that you're charging those socialized costs in the price when you buy them. And there's a lot of ways you can do this, but I'm particularly a fan of what's called the revenue neutral approaches to this, in which you return the money back to the taxpayers in the form of dividend checks so that it doesn't change the amount of total revenue that the government has at any moment, because all the revenue coming in for the carbon tax goes back out to the taxpayers. And this has bipartisan support for that reason. Groups like the Citizens Climate Lobby, I think I have it spelled out a little better here on this slide. The Citizens Climate Lobby, Students for Carbon Dividends is a great group of college students that's gotten behind this plan. And there's a whole group of conservative former Republican administration officials that have gotten behind this plan as well. And it's worth reading this. The idea is that by doing this, we incentivize the use of the carbon-free sources. The market will therefore get people coming in, moving to those future and existing technologies, improving them, moving to the future technologies faster. And the result is we'll be able to get rapid global change away from fossil fuels. And with that in mind, I want to close out by going back to something very similar to what we started with. I started with a tale of two planets, but now I want to talk about a tale of two futures on just this one planet. And the two futures, again, I want you to be thinking ahead to the year 2100. One future is suppose we just leave things alone, the status quo. What we see is this problem is so serious, it truly does pose an existential threat to our civilization. Just to be clear, so you don't think I'm overstating the case, I'm not saying we're going to go extinct. I'm not saying that everybody's going to die. What I'm saying is we will lose the kind of lifestyle and civilization comforts that we have gotten accustomed to. Those will no longer be available to our kids and our grandkids and the people of that year 2100. But that's not the only possibility. That's if we don't change what we're doing. The other possibility is, what if we do change? What if we put on that carbon tax and we rapidly move away from fossil fuels to sources that do not produce any greenhouse gases? In that case, I want you to think about what the year 2100 looks like then. Because by the year 2100, well, I can't say for sure we'll have nuclear fusion, but I would bet we probably will. And even if we don't have nuclear fusion, some of those other energy technologies we talked about, the biofuels, that solar energy from space, we'll have them. One way or the other, if we solve this problem and keep developing our technology, by the year 2100, we will have an incredible amount of free, not almost free, carbon neutral, no more global warming energy available to us. And if you think about what you can do with that, more energy at lower cost without pollution, if we use that properly, by the year 2100, we could have eliminated poverty. We could be desalinating water so that there's no freshwater problems. We could be mining the moon so we don't have to dig up resources from the earth anymore, and so much more. This is the choice we face. It's a choice between something very bad and not something of just okay, but something quite incredible. We have the possibility for an incredible future for today's kids and for our kids and grandkids if we act now. I want to show you this cartoon because it points out that I hope you believe me, but you can see what it says here. Somebody up at the front, this is from Joel Pett down in Kentucky, talking about all the great things that will happen if we do this. And somebody in the audience saying, well, what if it's a big hoax and we create a better world for nothing? Even if you still don't believe me about the dangers of global warming, this is a win-win situation. And then to contextualize it, what I'd like to have you imagine or actually do is write a letter to your grandchildren. And I realize most of you probably don't even have grandchildren yet, but you might someday. So, and in fact, 50 years from now, on average, your grandchildren will be your current age. So if you're a college student today, on average in 50 years, you'll have grandchildren in college. If you're a retired person today, on average in 50 years, your grandchildren will be retired. So dear grandchildren, put this in a time capsule for 50 years. As I write this in 2020, many people are arguing about whether global warming is a real problem, and if so, how serious it will be for you when you are my age. I have examined the evidence and I have decided to, and you write in what you're going to do right now about this problem. Hope your world is a good one. Love you. And ask yourself, what will your grandchildren say when they read what you did, having opened it up in the time capsule 50 years from now? I'm going to leave you with a couple of more quotations. This one from the other founder of modern conservatism, Ronald Reagan. He wasn't speaking specifically about global warming, but this is kind of like his letter to his grandchildren. What is a conservative after all, but one who conserves, one who is committed to protecting and holding close the things by which we live? This is our patrimony. This is what we leave to our children. And our great moral responsibility is to leave it to them either as we found it or better than we found it. And the last quote I'll leave you with is from someone more recent here, Greta Thunberg, age 16, Person of the Year for Time. And what does she say about this topic? She says, I want you to panic. I want you to feel the fear I feel every day. And then I want you to act. And I think this message is very important. This is not a message of despair. She's not saying, go panic, get all worried. She's saying, yes, but channel that into action. And if we all do that, we can build an incredible future for today's kids and our grandkids coming along behind them. So that's where I'll close. If you have more questions that I didn't get to today, the book is written in question and answer format, a global warming primer. It's posted for free online at globalwarmingprimer.com. I have a book on this topic for kids as well called The Wizard Who Saved the World, which you can see at the Big Kids Science website, and you can watch Japanese astronaut Koichi Wakata reading it from the International Space Station at storytimefromspace.com. And if you happen to be a middle school teacher or know middle school teachers, we have a climate chapter coming very soon in my free online middle school curriculum that is posted at grade8science.com. Please go there and check it out. And there you can see my other books and my Twitter handle, the Big Kids Science website. Thank you very, very much.
Thank you, Jeffrey. That was amazing. I could see why you've won all these awards for being a science communicator. Before I ask you some questions about climate change, just in the moment now, I mean, the topic that you're dealing with, climate science, it's got models, it's got complicated data, it's got technology, and you do a great job. You strip away the identity politics, you use down-to-earth language like too much of a good thing. This morning, the Wall Street Journal had an article, and it's not the first. There's been a whole series of articles that have critiqued the science communication about COVID and the pandemic, and saying somehow we're not communicating that science very well, and that's part of the issue, the public being confused. Do you have any thoughts about sort of the challenge of science communication in this pandemic?
Well, yes, the science communication has long been a big issue. And in the past, I think a lot of the blame fell on us scientists for not doing a good job at communicating things and making them clear in a way that the public could understand. The kind of a classic example you might see is if you think back to media, things you've heard about global warming, oftentimes the person speaking is giving so much detail that they assume people know that big picture 1, 2, 3 that I talked about, but they never actually say it. And then we tend to lose people in that way. So I think all of us as scientists need to do a better job at communicating the science and bringing it to a level that works. And there's a lot of people doing an excellent job of that now. Now, of course, today we're confronted with a new problem that we didn't have in the past, which is deliberate misinformation being spread through the media. That is a much more challenging problem, because even if we do a great job of explaining the science, if nobody hears it or they hear something from someone who's just outright misinforming them, that's a challenge for us to overcome. And I wish I had a good answer to that one, but I think the most important thing is for everybody who understands the importance of facts and science is go out there, talk to your friends, talk to your family members. You know, I realize when I give a talk like this, most of the people listening in probably already agreed with me. I hope maybe there were some people who didn't, and maybe I've convinced you. But you almost certainly know other people who have different opinions. Don't just let those slide. Talk to them in a respectful manner. Say, well, what makes you think this? And have you thought about this basic science argument and why it works? And have you looked at the data? And show them in a simple, respectful way. And you can convert people to understanding the difference between the real and the fake in that way.
Great, and that's why you use quotes from Ronald Reagan and Maggie Thatcher, just to draw that home, I think. So getting to the lecture you just gave, I love the way that you started off, and you were throughout, you paid attention to time span, time horizon, and what is it? Timing is everything, and everything is timing. But you wrote your book in 2016. It's 2020, and we have not done much. We're certainly on a path to have 1.5 degrees centigrade to maybe 2 degrees centigrade warming. And just to remind everybody, the centigrade Fahrenheit conversion, that's 3 to 4 degrees Fahrenheit warming. So we're on that path. You suggest that it's kind of bad economics why we haven't done anything. I'm wondering, there's another view out there, this what I would, as a cartoon characterized as the Naomi Klein view, which is it's a fundamental flaw of this growth economy and capitalism, and that we have to have a totally different economic system, not just a carbon tax to address this problem. How do you speak to that, what I would call sort of revolutionary view of changing society and our economic system versus the more moderate view and probably much more pragmatic view that you presented?
Well, I think the key word there is the pragmatic. I think one thing that we've seen over the last few years, with whether you agree with them or not, the Trump administration has overturned a lot of things that the Obama administration did. And whether or not you think that's a good idea, it proves that it is possible to overturn things that people did in the past. And so if you want a solution to climate change that is going to be a real and permanent solution, you have to have one that has broad, widespread public support. If it's only supported by 51%, it might pass in 2021, but then it might get undone in 2025. You have to have something that's got such large public support that it will stay in place. And the reason that I personally favor this, what you might call more incremental approach of the carbon tax, is because I believe it will get the job done when it comes to climate change. And I believe it can be done with that broad 60, 70, 80% of the population supporting it, that will ensure that once we start down this path, we won't turn around and go back.
Okay, there's you mentioned also in your talk, you brought up the melting ice, and then because of that loss of that reflected light, more heat being trapped in the oceans. You brought up fires. You didn't mention, but you also have methane released with permafrost thawing. So all those are positive feedback loops. In other words, warming causes more fires. Fires releases greenhouse gases, causes more warming. Melting ice causes more warming causes more melting ice. Permafrost thawing causes more methane release, causes more warming. So those are all loops, and there is some data saying we have an accelerating climate change, and these positive feedback loops and our awareness of them have got people talking more and more about geoengineering. In your book, you have a brief section about geoengineering and climate engineering, if you will, and you dismiss it because of the risk. And certainly when you wrote that book in 2016, that view was solidly entrenched, and I think all scientists shared that view with you. But now there's more and more discussion of it. Could you just talk about, should we consider it? Should we give it more serious conversation, climate engineering, given that even though it's not really the solution, it could short circuit these positive feedback loops? Or do you still hold to your 2016 view?
Well, I think I do think that it is worth continuing to explore it, because we should never give up on any possible options. We may find ourselves in a position where we have no choice. But I do think that, just as I said in 2016, I stand by, the problem that we face with geoengineering is there's basically two types of geoengineering, if you want to speak very broadly. One is geoengineering where you try to counteract the warming by things like putting aerosols into the atmosphere or giant mirrors in space and so on. And the problem with those is that they might work on the warming, but they still mean there's more carbon dioxide going in the atmosphere, which right off the bat means they do absolutely nothing about ocean acidification. And ocean acidification, in my opinion, is such a serious consequence of greenhouse emissions that if you don't deal with that, even if you've dealt with the other consequences, you still have a very, very bad problem. The other kind of geoengineering is geoengineering that would actually remove carbon dioxide from the atmosphere. And that I actually am totally supportive of. In fact, I think not only am I supportive of it, I think we need it, because I believe, as James Hansen has said, that where we are today, 415 parts per million, is already too high. We have to find a way to bring it back down, probably to like 350 parts per million, which means we're going to need that geoengineering technology to remove carbon dioxide from the atmosphere. So I think, we have to look at this as sort of a two-step problem. Step one is stop making the problem worse by getting away from fossil fuels. And that buys us some time to figure out how to do step two, which is develop that geoengineering technology to remove carbon dioxide from the atmosphere. The other geoengineering technologies, though, I don't see how they get around that fatal flaw of ocean acidification, but I do think they should keep trying. Maybe they'll come up with something that we haven't thought of yet.
Terrific. And I just wanted to, one last question, where the path of your lecture was a lot about the science and then getting into the solutions and really economics and politics and social change. I want to return to the science and you have such a mastery of a broad range of the hard sciences. What do you think are the basic gaps in our scientific knowledge, not gaps in our thinking about solutions, not gaps in our thinking about social change or politics, but what do you identify as scientific questions that if we answered them about climate change, we might be better off?
That's a very interesting question. I would say, in terms of the need for action and policy, we already know all the science we need to know. This is very simple science in terms of the basic stuff. The details are complex. But in terms of understanding the climate and where we go from here, there are many questions that we need to address scientifically. Number one, we need more data, and that's something that people are working on, particularly with the satellite missions and so on, like the GRACE mission that measures the ice loss in Antarctica and Greenland. The first GRACE mission went, it died, and then there was a year gap in data before they launched the replacements. We can't have those kinds of things. We need to have continuous data, more data. We need to have a better understanding of those feedbacks that you talked about, because those feedbacks, particularly things like the permafrost melting and releasing more greenhouse gas into the atmosphere, those are potentially very, very dangerous, and we don't understand yet at what point they start to really kick in and reach what you might call a tipping point, where we couldn't get back from it in a good way. We need to understand better the rate of ice melting so we can predict what future sea level rise is going to look like more. So there's many, many areas where climate research needs to continue and be expanded. And we need to know a lot more about the oceans and their response to all these things, and how we can then improve the ocean health so that we can protect the food that many people depend on and protect the species living in the oceans. So a lot of scientific research that needs to be done, but it won't affect the policy right now. The policy is very clear. We know we have a problem. We know we need to solve it. Margaret Thatcher knew we had a problem and needed to solve it in 1989. And you mentioned the fact that we haven't done much in the last 4 years since I wrote the book. I think even worse, we haven't done much since Margaret Thatcher gave that speech in 1989. Imagine if we had acted when she told us to then. We'd be living in a much better place today.
Well, thank you very much for a wonderful evening. And I want to put in a shameless plug for Jeffrey's books. They are really clearly written, and he has the essence of science. He does it with sometimes humor and a light touch. So go to his website and check out some of his books, especially for your kids.
Thank you very much.